So the public key is not secret, it's public. Like I said, it's derived from the private key, and it's really it's really a point on the elliptic curve calculated from the private key using elliptic curve multiplication. And the key point, the key aspect here is that the public key cannot cannot be used to derive the private key. It's only one way. You can derive the public key from the private key, but not the other way around. And this should be something obvious to the to the security, because otherwise, if the public key can be used to derive the private key, then there is really no security out there, right? So that's something to keep in mind. It's really fundamental. Now, let's take a look at what the Ethereum state is. Right? When we talk about the Ethereum state, it's really made up of objects called accounts. And each Ethereum account has a unique address associated with it. And this is a 20-byte address. And this is really used for for accounts to really address each other, to talk to each other. They need to know the address of the account that they're talking to, and it's really critical to how messaging works within the Ethereum protocol, and how the accounts engage in transfer of value or transfer of information. This is what enables it. Right? They need to be able to address. They need to be able to refer to each other using their address. Now let's take a look at Ethereum accounts. Ethereum accounts are fundamental to how Ethereum works, and each account has 4 fields in it. There's a nonce. It's really a counter that's used to make sure that each transaction can only be processed once, used to prevent replay attacks. There's a balance that is maintained in Ether. This is the amount of Ether that the account has at any point in time. And then there is contract code and contract storage. We'll look more into all of this, but this is at a high level what each Ethereum account contains. Account types. Ethereum has 2 account types. There is an externally owned account, or EOA as it is known as, and then there is a contract account. The EOA is an account that is controlled by private key, whereas contract account is an account that is controlled by the code that is contained within that account. EOA ownership. An externally owned account is controlled by a single private key associated with that account, like we just mentioned, and anyone who has that private key can create a digital signature that can be used to control the Ether that is present in that EOA. EOA, externally owned account. Recall that an account has 4 fields. It has a nonce, it has a value, code, and storage. But an externally owned account does not have any associated code or associated storage. It's controlled by a private key, as mentioned before, and that private key is used to create digital signatures from that account. And these signatures can be used to sign transactions from that EOA, which can trigger messages from that EOA to other accounts. And these messages can result in transfer of value, or they can trigger smart contracts. On the other hand, a contract account has the same fields, nonce, value, code, and storage, but in this case, it has associated smart contract code and associated storage. Smart contracts, and whenever the contract account receives a message, it triggers the code present in the contract account, and that runs the code and accesses any internal storage associated with it. And when the code runs, it can send messages to other accounts or even create new contracts. We shall see more about this in some of the forthcoming slides. Now let's take a step back and try to conceptually understand what are smart contracts. Smart contracts can be thought of as what are known as autonomous agents, in the sense that they're always present in the execution environment of the Ethereum blockchain. They're always ready to be triggered by a transaction or a message that is sent to them, and that results in the execution of the code that is present in their contract account. They have access to the Ether balance of their account, they have access to the contract storage, and the running of the code, the execution of the code, results in manipulation of this balance and the contract storage. Catchhack 256. This is the name of the cryptographic hash function that is used by Ethereum. Now, I'm sure many of you are already familiar with hashing functions, the concept of hashing, and specifically the concept of cryptographic hashing or cryptographic hashes that have very specific properties. If you don't, then just take a look, Wikipedia or any other standard cryptography reference that talks about what are the properties expected from a function for it to be a cryptographic hash function. So in the case of Ethereum, that happens to be Catchhack 256. This is really very closely related to the SHA-3, the secure hash function. SHA-3 was finalized as the standard by NIST, the National Institute of Standards and Technology. And in the case of Catchhack 256, it was the winning candidate for the SHA-3 competition. Now take a look at Wikipedia or any other reference for how hashing functions, the next generation of hashing functions are decided by this competition by NIST with entries from all around the world. It's a very interesting process. And in this case, Catchhack 256 was the winning candidate, but happens to be different from the finally adopted SHA-3 standard. So this is critical to a lot of the functioning of the Ethereum protocol and smart contracts. It's really a fundamental primitive to how computation in many ways is done on Ethereum. Externally owned account address. We touched upon this in some of the earlier slides, but an EOA, recall that it is controlled by a private key. And the private key is used to derive a public key. Right? It's a one-way derivation. You cannot go from a public key to a private key, but you can go only from a private key to a public one. And this public key is hashed using Catchhack 256 cryptographic hash function that we just talked about. And the output of that hash of Catchhack 256 is taken, and only the last 20 bytes, or in other words, the least significant bytes of the Catchhack 256 hash of the public key, are taken as the address for that EOA account. So this is how an address is derived from the private key. It's a very simple calculation, and it results in the address being 20 bytes or 160 bits. Now let's take a look at what is a transaction. Transactions are signed messages that originate outside the Ethereum blockchain. They are triggered by externally owned accounts that are managed or that are controlled by a private key, and the trigger happens to be the signature, the digital signature derived from the private key. These transactions are transmitted by the Ethereum network, and they trigger state change on the blockchain. and it's only transactions that can trigger a change of state. So Ethereum is fundamentally a transaction-based state machine. Now, what are the properties of such transactions on the Ethereum blockchain? The first key property of such transactions is that they're atomic. And what this means is that they run from the beginning to the end completely. It's either all or nothing. So the side effects of the transactions are only reflected on the blockchain if they run to completion. But if they don't run to completion, nothing that they do is reflected on the blockchain. It's as if the transaction never happened. So in other words, transactions cannot really be divided or interrupted with some of their partial state being reflected on the blockchain and the rest of it not reflected. That doesn't happen. That's really fundamental to understanding when you start looking at smart contracts and transactions that execute such smart contracts. This becomes something very critical to pay attention to. And this is different from your traditional computing environments where a particular process or a particular control might be interrupted, gets context switched out, and then something else, a different process or a thread executes, and then the original context is brought back in. So none of that happens within the context of Ethereum. That is not a property of an Ethereum transaction. A related concept is related property is that a transaction is serial, or transactions are serial. They're executed one after the other sequentially without any overlapping. There's no parallelism when it comes to the execution of transactions. So this is again critical to understanding and something that's specific to how Ethereum works. The third property is that of inclusion, transaction inclusion. So when a user submits a transaction, what is the guarantee that it gets included within one of the blocks on the Ethereum blockchain? This aspect is controlled by entities on the Ethereum blockchain known as miners. We'll talk a bit more about them. Miners run Ethereum nodes and they decide which transactions to include within a block on the blockchain. This depends on multiple factors, the key ones being the congestion on the Ethereum network, or in other words, the other or many other transactions that are competing for the same block space. It also depends on the gas price that the user decides to use for the particular transaction. The fourth property is that of ordering. Now recall that there are many transactions that are sent that get chosen by the miners and get included within a block of the blockchain. The specific order of the transactions included within a block is again chosen by the miners, and this, similar to inclusion, is determined by factors of congestion and gas price. So the key takeaway here is that there are entities known as miners on the blockchain who get to decide which transactions get included within a certain block and the specific order of the transactions within that block. Now let's take a look at what are the components of such transactions. Transactions are serialized messages, serialized binary messages, the format of which is really specific to the Ethereum network. They contain 7 components. The first one of that is a nonce. Nonce is nothing but a sequence number issued by the EOA, and it's used to prevent message replays. Right? Replaying the same transaction over and over again is prevented because the sequence number changes as part of the protocol for every such transaction. Then we have the gas price and the gas limit. Gas price is the amount of ether in Wei that is paid by the sender for every gas unit. And gas limit is the maximum number of gas units that the sender is willing to pay for this transaction. Then we have the recipient, which is really the destination Ethereum address for this transaction, the destination account that this transaction is targeting. And then we have value, which is the amount of ether in way that the sender is sending to this destination. We then have the data payload, which is of variable length. It's again binary encoded as per the format required by Ethereum that's sent as part of this transaction. Finally, we have the three components of the ECDSA signature, which are referred to as V, R, and S. We'll talk a bit more about each one of these 7 components that are used in this transaction in the forthcoming slides. So Nonce. Nonce is really an abbreviation for a number used only once. So this is really a sequence number that, as part of the protocol, is incremented in a particular fashion. And the use for the nonce, the application, is that it prevents replay attacks. This is something, if you have studied cryptography, it is very commonly used and for the same reasons is used within the Ethereum network as well. In the case of an externally owned account, this nonce value is equal to the number of transactions sent from that account. And in the case of a contract account, this nonce value is equal to the number of other contracts created by this contract account. Gas price. As mentioned, gas price is the price for every gas unit that the sender is willing to pay for this particular transaction. It's measured in weight per gas unit, and gas price is not fixed by the Ethereum protocol. The higher the gas price that the user or sender is willing to pay for this transaction, the faster that the particular transaction gets included by the miner into a block on the blockchain. And this price really depends on the demand for the block space at that point in time when the transaction is submitted. And the reason for this is that there is a limited amount of space in the block. So there's only a limited number of transactions as determined by the gas used by them that can be included within this block. And this might seem a bit complicated, but we'll see more of this in some of the forthcoming slides. The next component of a transaction is gas limit. This is the maximum number of gas units for which the sender is willing to pay for this transaction. And this really depends on the type of transaction that is being sent. If it is a simple Ether transfer, then it costs 21,000 gas units. But if it is a transaction that is targeting a particular contract, particular function of the contract, then that requires more gas. And if sufficient gas in the form of gas limit is not set for the transaction, if less than what is required is sent as part of the transaction, then it results in what is known as an out of gas error or exception, and that transaction fails. So the way it works is that for any transaction that is being sent by a sender, there is an estimated gas that needs to be sent as part of the transaction, needs to be paid for as part of the transaction. If that estimated amount of gas is not sent, if it is less than what is required, then it leads to the exception. But if there is more gas that is sent as part of the transaction, if there's excess gas than what is really used by the transaction, then the remaining gas is sent back to the sender. So this is really how the protocol dynamics work for gas for any particular transaction. The next transaction component is the recipient. This is the 20-byte address of the recipient account that the transaction is targeting. Now this could be an externally owned account address, or this could be a contract address. It really depends on the target of that particular transaction. And this could really be any address on the Ethereum blockchain or on the Ethereum protocol. And the protocol itself does not validate these recipient addresses in the transactions. So one can really send this transaction to any address, and that address might not even have a corresponding private key, or might not even have the contract that the sender expects to have. So all such validation should be done at the user interface level. Now, this concept becomes critical once we start looking at smart contracts and the addresses that they're interacting with, because that validation is really critical to some of the security concepts. And note that this recipient is really the target address, and there is no from address that is a component of the transaction. And the reason for this is because this address can be derived from the ECDSA signature components V, R, and S. They can be used to derive the public key, which in turn can be used to derive the from address. So this is something that you might see as missing from the transaction components, and this is really the reason why it is missing. The next transaction component is value. This represents the value of Ether that is being sent by the sender to the recipient. And what happens depends on the recipient being an EOA or a contract account. If the recipient happens to be an EOA, then the balance of that account will be increased by this value, and the sender's balance correspondingly decreases. If the recipient happens to be a contract account, then what happens depends on any other data that is present as part of this transaction. If there is data that is present as part of this transaction and the destination is a contract, then the data really represents the contract function that is being targeted. And the value of Ether that is being sent depends on the implementation of that particular function. But if there is no data that is being sent as part of this transaction and the destination happens to be a contract account, then the contracts receive or fallback function, if they were defined or if they are present, are triggered. And what happens with this amount of Ether, value of Ether, really depends on their implementation. Now, we haven't looked into what this receive and fallback functions are. We'll look at them a bit later. But at a high level, this is the flow that gets triggered. And if the contract that is being targeted does not have a receive or fallback function, then this transaction results in an exception. And if that happens, then this Ether that is sent as part of the transaction remains with the originator's account. The next component is data. This is the data that is being sent by the sender to the recipient. It's really relevant when the recipient is a contract account. And the data in that case contains the contract function that is being targeted by the transaction, and it also contains the specific arguments that are relevant for that contract function. The final transaction component is the ECDSA signature. This is 65 bytes in length. It has three subcomponents, V, R, and S. R and S really represent the signature components. They are 32 bytes each in length, adding up to 64 bytes. The final subcomponent is V, the recovery identifier. It's 1 byte in length. I would encourage you to look at one of the references provided to understand the reason why V is part of the ECDSA signature. Its value can be 27, 28, or it can be twice the value of chain ID plus 3536. Chain ID is the identifier of the blockchain. For Ethereum mainnet, chain ID is 1. We'll see a bit more about this in some of the future